Hi everyone, welcome to Career Avenues. My name is Vaishnavi and today I will be your faculty for climatology. And today will be an introductory session to what climatology is, what all topics we can cover and what is important to GATE. So let's just, before we jump in, I'll tell you a little about me and how I teach. I don't do presentations as PPTs and slides. I have some keywords and I'll be writing all the explanations and all the keywords, and I'll tell you what all is important as well. So I suggest you have your own notebook, your own pen, and make your own notes, because this will be your Bible or your ultimate study guide. Better than any textbook is your own notes, because that's what you'll be using for the next year, until the next year. So maintain good and clean notes. And I have a bad handwriting, so I'm trying to improve. If you don't understand anything I write, just stop me and message on the chat. And any concept you don't understand or any words that you don't understand, again, just put a message and we'll clear it out, okay? So let's start this first session about climatology. Firstly, let's look at what part of GATE it will come in. According to the syllabus, we have now we have architecture and the planning parts for GATE architecture paper. And under the climatology topic actually comes in architecture and the common part as well. Under architecture, you have things like thermal comfort, some thermal quantities, principles of thermal design, solar architecture, and natural ventilation. The common part has a lot more theory in it, and it's almost general knowledge. It's what you would have probably learned in your BArch, which is climate responsive design, passive design techniques, climate zones of India, and climatic factors. Okay. So now, what I would suggest is you mention the architecture and make notes as well, architecture part 2, because what we have seen is this, the papers that have been coming in architecture and common part is quite recent, right? So some of the questions that in the syllabus comes in the common part, sometimes they've asked in the architecture, and some syllabus questions that were supposed to be in architecture part is there in the common part. So just focus on everything, have a basic understanding. So you'll learn and you'll be able to answer no matter what part it comes under. Okay. So as to the type of questions that are seen in GATE from climatology, you have both theory questions. Theory questions are mainly seen in these common parts, but they're also there as a good weightage from the architecture part. And you also have numerical type questions. Numericals are mainly seen from these topics that are there in the architecture. The formulae, equations, and the units, everything will go through. You have to pay a little bit attention to, especially things like thermal quantities. We'll get there. We'll try to cover that in the next session. And the numericals are quite easy. And you'll also, in theory part, you will also have multiple choice questions or multiple select questions. I hope you know what these are. Multiple choice questions will be, the questions have 4 options and only one option is the right answer. The other 3 are wrong. The other 3 will give you a negative marking. Multiple select questions are those where more than one option, either 2, 3, or 4 sometimes are correct. And this usually does not have negative marking. Numerical answer type questions where there is no options, they'll just give you a blank and you'll have to enter a numerical value within a certain range. And this usually also has no negative marking. And the weightage that we've seen so far from this topic, climatology, is usually between 5 to 7 marks in the question paper. Okay, so it's quite a good chunk of the marks you need, and it's easily scoreable if you understand the basic concepts behind and some terms and definitions. It's very doable and you can easily score 5 to 7 marks. So let's move on to the first topic, which is thermal comfort. Today we'll be covering thermal comfort specifically from the architecture part. So let's move on. So under the first topic, under thermal comfort, we have something called a deep body temperature. So now first, let's understand what is thermal comfort. When you say thermal, it's always something to do with heat. Correct? Like thermal gain, thermal mass, whatever it is, it's always something to do with heat. This is your keyword. The word comfort is always with respect to humans or occupants. Right? So when we say thermal comfort, we're trying to see what in terms of heat. Back on the first slide. Okay. Yeah, here we're just talking about the type of questions that will come in the GATE exam, which is theory and numerical. Theory questions will be there both in the architecture as well as the common part. And there'll be MCQs and MSQs, multiple choice and multiple select. No problem. It's okay. So can I move on to the next slide? Okay. So yeah, as I was saying, the words thermal and comfort talk about how and where in what environments humans or occupants will feel comfortable with respect to heat. Okay. So maybe it's too hot, it's too cold. All of these are words that you use to express thermal comfort. So we are talking about humans. So when we say deep body temperature, it's talking about a core temperature of the human body. So this is the temperature that your body has to maintain for it to function normally. So remember, if you know, when we have fever, we say we have a high body temperature. And when we have a low body temperature, also we're very freezing. So the body has to maintain a proper stagnant temperature, which is, can anybody try and guess what the temperature is that we maintain? Like when you measure with a thermometer when you're healthy and without any fever, can you tell me? Yes, exactly. It's 37.4 degrees Celsius or 98 degree Fahrenheit. So this is a constant temperature that the human body has to maintain. Anything above, we have very bad threshold. So even like 1 or 2 degree increase in temperature means we're all very uncomfortable with fever. We take pills and tablets. So it's very important for the body to maintain this temperature. But because we're always in an environment where we lose or lose or gain heat, there is always interaction with the environment. So there are different ways in which we interact with the thermal environment, where we gain and lose heat. So how do we do this? Any body, not just the human body, any kind of mass or a physical object will gain and lose heat in mainly 3 ways, which is conduction, convection, and radiation. Even the human body will gain and lose heat to the environment in these 3 ways. Conduction is not so much because we don't really interact with, we constantly interact with surfaces. I hope you know what these 3 terms are: conduction, convection, and radiation. Conduction is a heat transfer between physical surfaces. So when 2 solid objects are in contact with each other, there is a heat transfer from one to the other. That is conduction. Convection happens when there is a medium between 2 objects. So if you have object A, object B, and there is a medium of air or water or some kind of a fluid, heat transfers through that medium, and that is convection. Radiation is when the body itself emits heat. So like the sun will radiate heat. This is radiation. This is a basic, high school physics, just brushing up. So all the terms that we speak later on will be familiar to you. So now even the human body will gain and lose heat in these 3 different ways. Apart from this, there will be other physical processes like evaporation, and metabolism there. See how these all affect the human temperature. Good evening. I hope you remember yesterday's class. Today is going to be a continuation of it. And just like yesterday, I don't have any PPT with continuous text or anything. I will be having keywords and explaining each concept as we go one by one. Today's class will have quite a bit of numericals. So today we'll be covering, we finished thermal comfort yesterday. So today we'll be looking at thermal quantities and principles of thermal design. If time permits, then maybe a little bit of solar architecture and natural ventilation. Okay. So today I would suggest you all have a calculator with you because today we'll be doing some numericals. And a suggestion while doing numericals is when you're taking down your notes and when you're solving the numericals here, try not to skip any steps, okay? Write down each step one by one so that it's clear for you when you look at it next time. And if possible, I'll give you enough time so you can note down the question as well. So when you later look into your notes and refer them, you'll understand how you've solved the question and what the question is about, okay? Secondly, we'll be covering quite a few formulae formulae, right? So there'll be a lot of new terms and focus on the units of each of these terms that will help you with the formulae, and we can solve numericals using that. Okay. So just like yesterday, let's first start with some key terms and definitions. Okay. First one, we're looking at thermal quantities. Again, thermal has always meant heat. Yesterday we saw dry bulb temperature and wet bulb temperature, right? So what exactly is temperature? It is simply a measurement or a degree of intensity of heat. It simply measures how hot or cold a body is, right? So it's simply hot or cold. And if you quantify this in a scale, that becomes your temperature. And how do you measure temperature? Using a thermometer. Instrument used is thermometer. Now, there is more than one units through which you can measure temperature, right? We all know the SI unit. Can you tell me what the SI unit of temperature is? Anyone knows the SI unit? Which is a standard metric system that we follow while doing any kind of calculations in physics. Take a guess. Okay, what all scales do you know at least? You know there is a Celsius scale. Okay, Fahrenheit, yes. Fahrenheit is one scale. There is Kelvin, correct? Yes, SI unit is Kelvin. And there is one more scale, which is a Celsius scale. This is what we're mostly familiar with when we talk about outdoor temperature, etc. Right? So now there is obviously has to be a conversion between all of these three scales, which is degree centigrade is equal to Kelvin minus 273.15, which is equal to degree Fahrenheit minus 32 into 5/9. This is a formula for you to convert a temperature between different scales. Okay, so make a note of this formula. If you have a temperature given in centigrade, you can easily convert it into Kelvin or into Fahrenheit, right? So if you add 273, it becomes the Kelvin scale, right? Centigrade plus 273 is Kelvin when you put 273 this side. Or if you use this formula, you can convert it into Fahrenheit. There have been some questions in GAST where they've directly asked, 33 degrees Celsius is dash Fahrenheit. All you have to do is remember this formula and it's easily 1 mark for you. Okay. The next term that we're going to look at is heat. Again, we've dealt with heat yesterday, heat transfers, thermal, right? That's all we're talking about in climatology right now. But the definition of heat is that it is a form of energy, first of all. Energy. So whatever we're measuring here, no, what is hot or whatever is cold is because of heat. It's simply a form of energy. Can anybody tell me what the unit for energy is or heat? How do we measure heat? Correct. It's joules. Joules, or short form is capital J. Okay. So this is how we measure heat. Apart from joules, just like how temperature has different scales or different kind of units, even heat has different units. So one of them is BTU, which is called British Thermal Units. Okay. This is usually used when we are talking about, say, heating capacity of a heater or refrigerator, cooling capacity of a refrigerator. All of these are actually measured in BTU in the commercial world. Apart from this, there is also kilocalorie. This is mainly when like combustion happens, like calorific values of say substances when they burn, etc. Again, there is a conversion formula between all of these, and that is 1 BTU or British thermal unit is equal to 1055.06 joules, and 1 kilocalorie or kcal. So kilocalorie is written in small kcal. Okay, is equal to 4184 joules. This is the conversion between all of these three units. You can keep this in mind. If you can, try and learn to remember, but otherwise we usually use joules because it's the SI unit, and this is how all of the other units are also expressed in terms of joules. Sometimes we do use kilocal and BTU, but for Gates perspective and from architecture perspective and climatology wise, they don't really come out that often, but it is very well and good if you can remember the conversion values. Any doubts till now? All right, so we just learned the concept of a multi-layered wall, right? I'll read out the question. I'll give you 5 minutes to solve. You can, if you find the answer or if you know how to do it, go ahead and post the answers, and then I'll solve the questions with you. A brick wall, 19 centimeter thick, keep an eye on the units, has a thermal conductivity of 0.811 watt per meter degree centigrade. The outside and the inside surface conductances are 16 watt meter square degree centigrade and 8 watt per meter square degree centigrade respectively. The U value of the wall, so they're asking for the U value of the wall in watt per meter degree, watt per meter square degree centigrade is watt. Okay, so take your time and solve step by step, write down everything very neatly because you will have to come back and refer these notes. Take your time and solve them. I'll give you time. Was anybody able to solve it? You can just type your answers and put it here. Okay, Tanmay says 0.1184 B3. I'm sorry, I don't know your name. You say it's 2.3. One more thing is when you're solving numericals, no, in GATE, especially when you have many times you're calculating, always calculate till the third decimal place, third or fourth. And the final answer, you can always round it off to 2 or 3. Usually in the question for numericals in GATE, they'll tell you till what decimal you can round it off. But when calculating, always write and calculate the third or fourth decimal place. Okay. Any other answers? Okay, I'll solve it with you now. Let's see what we have here. Okay, we say 19 centimeter thick. A brick wall has 19 centimeter thickness. So L is 19 centimeters, which is, did you take 19 centimeters while writing the answer? Is 0.19 meters. We have the first one. Thermal conductivity, capital K, is 0.811. Okay, one more, 2.3 as the answer. 0.811 watt per meter degree centigrade is your thermal conductivity. Outside and inside surface conductances. So SCO is 16 watt per meter square degree centigrade. SCI is 8 watt per meter square degree centigrade. 2.37 watt per meter. Okay, let's see. Right. So what's the next step? We have all of the information. We need to find out the U value. Luckily for us, it's just one layer of brick wall. There's no extra plastering and all, but we do have surface conductances inside and outside. So the first thing we need to do is find the R value of the entire component. R wall is equal to, they've given surface conductances, right? So you can directly write 1 by SCO plus R1. Sorry, and R1 is actually L by K, right? So R is equal to L by capital K. So I'm going to directly write L by K here plus 1 by SCI. Substituting the values, what do we get? 1 by SCO is 16, 1 by 16, sorry, plus L is 0.19 by 0.811, which is K, plus 1 by 8. Right? What is the R value everybody got? This will be 1 by 0.0625, correct? Plus 0.19 by 0.811 will be 0.234 plus 1 by 8. Have your calculators ready because next also we have some questions. Plus 0.125. Okay, what is your R value? Okay, we are getting R value of the wall as 0.4. I think we get 0.421, no? No? Cross check, please. Yes, okay. 421 and until the third decimal, if it's right, it's proper, okay? Meter square degree centigrade per watt. Now we've got the R value. So U value is simply 1 by R watt. What is the answer we're getting? 1 by 0.424215, right? Which is, you should be getting 2.372. watt per meter square degree centigrade. Okay, this is your answer. Did everybody get it?